Welcome to our deep dive. Today, we're tackling something pretty wild, Kolmogorov-Arnold networks, or CANs for short. They're like neural networks, but reimagined through the lens of a really cool mathematical theorem.
Yeah. And the research paper we're looking at is packed with some pretty complex math, but it's definitely worth it. What CANs could potentially do is pretty amazing,
Yeah.
boosting accuracy, interpretability, even helping scientists discover new laws of physics.
Okay, so we've got our work cut out for us, but hey, that's what a deep dive is all about, right? So let's start with the foundation, this Kolmogorov-Arnold theorem that the paper keeps mentioning. What's that all about?
Well, imagine this. Any continuous function, no matter how many variables it has, can actually be represented as just the sum of single variable functions.
Wait, really? So even something super complicated can be broken down into simpler parts. That's kind of mind-blowing.
It is pretty elegant, right? And this idea, while not new, has been really hard to use practically in machine learning until recently.
So why is that? What changed?
Well, those single variable functions, the ones the theorem talks about, they can get really messy and hard to define computationally. But recent advances in computing power and techniques like backpropagation have made it possible to finally leverage the theorem.
And that's where cans come in.
Exactly. They take this theoretical idea and turn it into a working neural network. They're structured with layers, kind of like traditional multi-layer perceptrons, MLPs. But instead of fixed activation functions on each node, they have learnable activation functions on the edges.
Okay, I'm looking at figure blight 1 in the paper, and I can visually see the difference. It's almost like they've shifted the complexity from the nodes themselves to the connections between them.
That's a great way to put it. And this shift has some really interesting consequences. For example, CANs often need way fewer parameters than MLPs to achieve the same level of accuracy.
So they're more efficient. That's pretty impressive. The paper mentions that cans can achieve better scaling laws than MLPs, meaning their error decreases faster as the network grows.
Yes, and it's not just theoretical. They show how a small CAN outperforms a much larger MLP. When trying to fit the complex Bessel function in figure 3.1, this better scaling, it's been shown to hold true even when applied to solving a Poisson equation, which is a fundamental equation in physics.
Okay, that definitely catches my attention. Smaller networks, better performance.
I'm starting to see why these CANs are so interesting, but the paper also highlights their interpretability. What does that mean in this context?
So with traditional MLPs, it's hard to know what's going on inside. They're like black boxes. But with cans, you can actually visualize those learnable activation functions on the edges and see which input variables are most important for a given task.
So you can peek under the hood and understand how the network is making its decision.
Exactly. And not only that, you can actually simplify a can after training to reveal the underlying symbolic relationships in the data.
Really? The paper mentions an example where a CAN rediscovered the equation for relativistic velocity addition just by analyzing the data, right? That's right. It's shown in figure 4.1. It's pretty remarkable what this implies. Imagine being able to use CANs, not just to make predictions, but to uncover the hidden mathematical or physical laws governing a system.
Wow, that's pretty profound. It's almost like giving a neural network the ability to do scientific discovery on its own. So let's dive into some of these real-world applications. The paper mentions some really interesting examples in knot theory and physics, right?
Yes. Let's start with knot theory,
Yeah.
the study of those tangled loops. But in mathematical sense,
And how do cans fit into this world of knots?
well, they took a CAN and trained it on a data set of knot invariants, which are essentially properties used to describe and classify knots. And get this, the CAN was able to rediscover a relationship between those invariants. That had only recently been proven by mathematicians. It did so just by analyzing the data. It's visualized in figure 4.3.
So it's like the can is independently doing mathematical research. That's wild. And what about the physics examples? They mentioned something about Anderson localization.
Right. Anderson localization describes a situation where disorder in a material can cause electrons to get trapped. The researchers applied CANs to 3 different physics models exhibiting this localization. And what's really fascinating is that the CANs were able to very accurately pinpoint the mobility edge in each model.
Mobility edge. What's that?
Think of it as the energy level that separates localized electrons from those that can move freely. It's like a critical point or a phase transition, similar to water turning into ice. Figures 4.5 and 4.6 show how accurately the CANs were able to identify this critical point.
So they're not just identifying patterns, they're uncovering the underlying physics behind these transitions. That's incredible.
It is. The researchers even describe a scenario where a hypothetical physics student named Alice could interact with a can to test hypotheses and further refine their understanding of the system.
That's a really interesting concept, this idea of collaborating with an AI to do science.
Exactly. And it highlights one of the key advantages of cans.
Yeah.
Their interactivity. They're not just static models. Users can manipulate and interact with them to guide the learning process.
Okay. I'm definitely intrigued by this idea of interactive AI, but I think we're ready to move on to part 2 of our deep dive. Join us as we get into the nitty-gritty of how these cans actually work.
We'll be back soon to unpack the technical details.
Welcome back. Last time we covered what makes cans unique, but now I'm ready to get into the details. How do these things actually work?
Well, it all comes down to those learnable activation functions on the edges. They're represented as splines. Think of splines like building blocks for smooth curves. You could adjust each block individually without messing up the rest of the curve.
Okay, so each edge in the network has a spline function that can be adjusted to control how signals pass through. That sounds pretty flexible.
Exactly. And that flexibility allows cans to approximate very complex relationships within the data. Now, the researchers use a specific type of spline called B-splines for computation. But the key concept is that these functions can be adjusted locally.
The paper also mentioned grid extension, which sounds pretty technical. What's the point of that?
Think of it like increasing the resolution of an image. Those splines are defined by a set of points called grid points. By adding more grid points, you essentially allow for more fine-grained control over the spline function, making it more capable of capturing subtle nuances in the data.
So it's like giving the network a more detailed map to work with. Does that make it more accurate?
It absolutely does. In fact, Figure 2.3 shows how the training loss, which is a measure of how well the network is learning, drops dramatically every time they extend the grid. And the beauty of this approach is that you can do it on the fly without having to start the training process over.
That's pretty slick. Traditional MLPs don't have this kind of flexibility, right?
Right. With MLPs, if you want to improve accuracy, you typically need to add more layers or nodes, which can be computationally expensive and require retraining the whole network. Grid extension offers a much more efficient way to fine-tune a can.
Got it. So we've got these flexible spline functions, and we can make them even more precise with grid extension. But the paper also mentioned techniques for making cans more interpretable, like simplifying their structure. How does that work?
One key technique is sparsification. Essentially, they encourage the network to use as few activation functions as possible. They do this using a combination of L1 regularization, which penalizes the magnitude of the spline functions, and entropy regularization, which favors simpler representations.
So it's like they're saying, hey, network, only keep the most important connections and try to stay compact. Does that really make a difference?
It makes a huge difference in terms of interpretability. You can then prune the network, which means removing nodes that aren't contributing much. Figure 2.4 shows how much simpler a prune can becomes compared to its unpruned version.
It's like you've trimmed away all the unnecessary branches, leaving a much clearer structure. And that makes it easier to understand what the network is actually doing.
Exactly. You can trace the flow of information much more easily and see which input variables are driving the output. This level of transparency is invaluable for building trust in AI systems.
Now, I remember you mentioned a hypothetical physics student, Alice, using a can to understand Anderson localization. How does that example showcase this interactivity?
Alice could interact with the can by using her knowledge of physics to guide its learning process. She could simplify the network structure, impose certain constraints based on her understanding of the physics, or even suggest potential forms for those spline activation functions.
So like a two-way conversation between the human expert and the AI. That's a pretty cool way to think about it.
It is. And this idea of collaboration is really at the heart of what makes cans so exciting. They're not just passive tools. They can be active partners in the process of discovery.
Now, all of this brings us to the bigger picture, right? Where do cans fit within the broader trends of AI research?
That's a great question. Cans align with two key trends: neural scaling laws and mechanistic interpretability. Neural scaling laws essentially tell us that bigger models and more data usually lead to better performance. However, that can become computationally very expensive.
So efficiency is becoming more important.
Absolutely. And that's where cans shine. Their efficient use of parameters suggests they might achieve better scaling laws than traditional networks, requiring less computational power for the same performance. The second trend, mechanistic interpretability, focuses on understanding the how and why of AI decision-making, rather than just focusing on the output.
So it's like we're not satisfied with just getting the right answer anymore. We want to understand the reasoning behind it.
Exactly. And the transparency of cans makes them a perfect fit for this. Their structure allows us to trace the flow of information and understand how individual components contribute to the final decision. This level of transparency is essential for building trust in AI, especially as it becomes more integrated into our lives.
This has been a fantastic deep dive into the mechanics of cans. I'm really starting to grasp how these things work and why they're so groundbreaking.
I'm glad to hear that. And in part 3, we'll explore the implications of all this, how cans could shape the future of AI and impact our world.
So we've explored the mechanics and inner workings of cans, but what does it all mean? How could this technology actually change things?
That's the big question, isn't it? While it's early days for cans, I think their potential impact is huge, particularly in scientific research. We've already seen how they can rediscover known relationships and even uncover new ones.
Right. Like that example of the kin. Finding a relationship between knot invariants that mathematicians had just recently proven. It's almost like giving scientists an AI research assistant that can sift through data and highlight the key insights.
That's a great analogy. Imagine physicists using cans to analyze data from particle accelerators, or biologists using them to understand the complex interactions within a cell.
Yeah, and it's not just about finding new information, it's also about making complex scientific findings more accessible to people who aren't experts in the field.
Exactly. That's where the interpretability of cans becomes so important. Imagine being able to translate complex equations and jargon-filled research papers into intuitive visualizations that anyone can understand.
Yeah, it could really democratize scientific knowledge. That's an exciting thought. But let's shift gears a bit. How might cans affect our everyday lives outside of scientific research?
Well, one area where they'd have a huge impact is in building more trustworthy AI systems. Remember how we talked about the transparency of cans? How they allow us to understand their decision-making process?
Right. It's like being able to see the logic behind the AI's choices, which builds trust, especially as AI becomes more integrated into our lives. That transparency is going to be crucial.
Absolutely. Think about self-driving cars. That can explain their decisions in real time, or medical diagnosis systems. That can provide clear justifications for their recommendations. That level of transparency would make people much more comfortable relying on AI.
It makes sense. If you can understand how the AI is working, you're more likely to trust it. But beyond trust, cans could also lead to AI experiences that are much more personalized.
Exactly. Remember, cans can be interactive. Users can actually shape the AI's behavior to suit their specific needs and preferences.
So it's like having an AI that's truly tailored to you. That's a powerful concept. It seems like there's a lot to be optimistic about when it comes to cans. But are there any potential downsides we should be aware of?
Of course. Like any technology, cans have potential risks. One concern is that the very interpretability that makes them so appealing could also be exploited.
I see what you mean. If someone can understand how the can works, they might be able to manipulate it or find ways to trick it.
Exactly. Researchers need to be very careful about security and robustness. As cans are developed and deployed, we don't want this technology being used for malicious purposes.
That's a good point. And there's also the issue of accessibility. If cans require specialized knowledge or expensive computing resources, they could end up benefiting only a select few.
That's right. It's crucial that we prioritize equitable access to this technology so that everyone can benefit from its potential.
So there's a lot of responsibility that comes with this powerful technology. We need to use it wisely and ethically. But overall, I'm really excited about the possibilities that cans offer. It feels like we're on the cusp of a new era in AI.
I agree. Cans, with their emphasis on transparency and collaboration, could help us build a future where AI is not something we fear, but a partner that helps us understand the world and achieve our goals.
Well said. And on that note, we've reached the end of our deep dive into the world of Kolmogorov-Arnold Networks.
It's been a pleasure exploring this fascinating technology with you.
Thank you for joining us. We hope this deep dive has sparked your curiosity and inspired you to learn more and